When a substance that is typically thought of as being insoluble is placed into water, some of that substance will actually dissolve. And if it's in pure water, there's a certain amount that is capable of being dissolved. It's usually a very small amount. And so if we take the example that you see here in the chart, calcium fluoride, we can see that in pure water, the solubility of calcium fluoride in moles per liter is little more than 10 to the minus fourth power, or 1/10,000th of a mole per liter. Not very much at all. And so what we see then is that as another substance, sodium fluoride, is added, we see that that molar solubility of calcium fluoride drops off dramatically. And that drops off because of something known as the common ion effect. And so when you have an equilibrium, and then you introduce something to that equilibrium system that is going to contribute one of the ions that's present in the equilibrium, the effect that it has is it will decrease the solubility of the salt in the solution. And so in the case of calcium fluoride, the addition of anything that produces or contributes either calcium ions or fluoride ions will create this effect. And so the addition of sodium fluoride has the effect of decreasing the solubility of calcium fluoride. So calculating solubility when a common ion is present is very similar to what we've done with our rice tables before. So we start off with the question, what is the molar solubility of calcium fluoride in a solution that is 0.010 molar calcium nitrate? And so if we write the expression for calcium fluoride, we can see that when calcium fluoride is introduced into water, it quickly comes to an equilibrium where the solid is favored, but there is a little bit of calcium ion and two fluoride ions. And so if we write the KSP expression, we know that the KSP expression is just a special type of equilibrium constant expression, so products over reactants, but only things that are aqueous in solution or gas phase are included in that K expression. So the only species that we see are those ions on the product side. So we have concentration of calcium ion times concentration of fluoride ion squared because of the coefficient 2. So we set that expression equal to the KSP, which we're given is 3.9 times 10 to the negative 11th. So if we set up a rice table, okay, again, the calcium fluoride column will have no values in it because it's a solid. The concentration doesn't change. But here's where the presence of that calcium nitrate makes a difference. Because there is 0.010 molar calcium nitrate, that ionic substance will dissociate completely. And because the stoichiometric ratio is 1 calcium ion for every 1 calcium nitrate, that means that we have 0.010 molar calcium ion present to start. We don't have any fluoride ions to start. And so that's why we see the values that we do in the I row. So as the calcium fluoride would be introduced, a certain quantity, X, will be able to dissolve. And so we would say that calcium ion concentration would increase by X, and the fluoride concentration would increase by 2X because of that stoichiometric ratio based on the subscripts in the formula for calcium fluoride. So coming up with our equilibrium concentrations, that'd be 0.010 X plus X and 2X for the fluoride ions. So taking those values for the equilibrium concentrations and putting them into the KSP expression, we get 3.9 times 10 to the negative 11th equal to 0.010 plus X, that's for the calcium ion, times 2X squared, the 2X being the concentration of the fluoride ion. And so because our KSP value is so small, we can make the assumption that X is very, very small, much smaller than the 0.010 moles molar concentration that we have to begin with. So what we can do is assume that X being much, much less will allow us to assume that the equilibrium concentration is still pretty much 0.010. So that makes the math a bit easier to work with. And so we plug those values in, we solve for X, and we come up with 3.1 times 10 to the minus fifth molar. So here are some typical questions, types of questions that you might encounter. First one, of the substances below, which one will decrease the solubility of lead-2 cyanide in a saturated solution? And so with lead-2 cyanide, right, we know that that is going to, we would have lead-2 ions and we would have cyanide ions. Okay, two of them in fact. But the ions themselves, that's what we are interested in terms of common ion effect. So what we want to do is we want to look at each of these and determine, are either of these ions going to be produced by these materials being found in solution? And so the first one we see, definitely there's some lead there, and it is lead-2. If we do the math here, we would get lead-2 ion present in that first solution. So that one's a definite. If we look at the rest of these, sodium permanganate, no lead, no cyanide. Permanganic acid, no lead, no iron, or cyanide. Hydrogen peroxide, no lead, no cyanide. Sodium chloride, no lead, no cyanide. So the only substance that is listed here that would give us a decrease in solubility would be the lead-2 permanganate. The next question, in which aqueous system is calcium fluoride least soluble? So the first thing that we can do with this is we can eliminate water. And the reason we can eliminate water is because we know that in pure water, there are no common ions present. So that means that your substance would be its most soluble when it's in pure water. So we want the least soluble, so we're going to get rid of water right off the bat. Okay, so here we have calcium ions, so Ca plus 2, and we're going to get 2 fluoride ions. So we're looking to see, are any of these things going to contribute calcium ions or fluoride ions? And so the first one, hydrofluoric acid, it's a weak acid, but it will produce some fluoride ions. So that's a possibility. Okay, again, hydrofluoric acid, so the option C here is another possibility. Nitric acid, HNO3, okay, not producing calcium ion, not producing fluoride ion, so that's not going to give us a common ion. And then 0.8 molar of the potassium fluoride. Again, that is a soluble salt, so that's going to give us fluoride ions. So now we have 3 potential contributors of common ions. Now we need to look at the concentrations, because the one that's going to be the least soluble is going to be the solution that provides the most fluoride ions right off the bat initially. And because all of these are in a 1-to-1 ratio, okay, and again, the hydrofluoric acid ones are weak acids, so there's going to be an equilibrium there as well. But the potassium fluoride is a strong electrolyte, and so because of that, we're going to see 0.8 molar of the fluoride ion. That is going to be the highest concentration, so that would have the greatest effect and make calcium fluoride the least soluble. All right, next example, in which of the following aqueous solutions would you expect lead-2 chloride to have the lowest solubility? Again, looking for lead-2 ions and looking for chloride ions. Okay, 2 of them when that dissociates. And so in the first one, we see chloride is present. That 2 should be subscripted. But we are going to get chlorides, all right, specifically 2. Here we're going to get lead, right? So that's lead plus 2. Here we're going to get a chloride, just 1. And here we're going to get a chloride ion. So all of these, save for the pure water, okay, that one we can eliminate because we want the lowest solubility. All right, now we need to look at our concentrations and take that into account. Well, they're all 0.020 molar solutions, so here's where we have to take into account the stoichiometry that comes about from the subscripts. And the barium chloride, because it produces 2 chlorides per barium chloride that is dissolved, that means that our concentration of chloride would actually be 0.040 molar. So therefore, that solution will cause PbCl2 to have the lowest solubility. All right, for the last example, I went ahead here and kind of broke things down a little bit. We know that silver bromide, we're going to be looking for common ions of silver and bromide, and looking at the formulas for the substances, the solutions that we would be putting the silver bromide in. We can see the common ions that are produced. Pure water is excluded because, again, there's no common ions present. And so we see that in the strontium bromide, we actually get 2 bromide ions. And when we take that into account with the molarity of the solutions, we would get 0.080 molar concentration of the bromide ion. So that would be the greatest interference and therefore lower the solubility of the silver bromide the most. All right, so the question is determine the molar solubility of AgBr in a solution of 0.150 molar sodium bromide. We've got the KSP of AgBr, and that's 7.7 times 10 to the minus third. So we're going to start by writing our expression for the silver bromide. So we're going to have AgBr solid in equilibrium with, I apologize for the slant here, silver plus bromide minus, and we'll set up our ice table, so ICE. Okay, again, the silver bromide, no values there. Silver, okay, because we have sodium bromide present, that's going to dissociate to give us sodium ions and bromide ions, and it's a 1-to-1 ratio, 1 bromide for every sodium bromide. And it's a strong electrolyte, so it's going to dissociate completely. We're going to get 0.150 molar bromide that's produced and present in the solution right off the bat. No silver ion to start. Okay, so now the silver bromide, as it's added, whatever amount does dissolve, we're going to represent that with X. So this is going to be plus X, and bromide would also be plus X because they're both in a 1-to-1 ratio. So our equilibrium concentrations are X for silver ion and 0.150 X for bromide. All right. Now, because the KSP is so small, we can assume that X is much, much less, all right, than 0.150. And so if that's true, that means that we can essentially, actually this should be plus X times X, all right? We can assume that the concentration of bromide at equilibrium is still going to be 0.150. So if we plug everything in, 7.7 times 10 to the minus 13th, that's our KSP, equal to the concentration of silver ion, so that's our X, times the concentration of the bromide ion, which is just going to be 0.150. And I use brackets instead of parentheses. Hope you forgive me. But when we do the math there, we should come to 5.1 times 10 to the minus 12th. So a practical way that we can use the KSP is to evaluate whether or not a precipitate will form when we mix 2 solutions, particularly solutions that we might ordinarily predict with the solubility rules that are going to be insoluble or even slightly soluble. But we can see that if the concentration is low, then we might actually be able to get some dissolved and not have a precipitate form. And the whole premise here is we compare the actual concentrations at the moment through the reaction quotient with what that KSP value is. So if we calculate with the actual concentrations and we find that the Q value is equal to the KSP, then we're at a state of equilibrium. And we would not find a precipitate there because we would have a saturated solution. If the Q value determines to be that it's less than the KSP value, then that means that the forward reaction would be favored, which is the dissolution direction. So that means that no precipitate would form in that case either. But if Q evaluates greater than K, then that means that the reverse reaction will be favored, which is the insoluble solid, and therefore we would expect to see a precipitate form. So if we look at these 2 examples, if 300 milliliters of 1.0 molar lithium hydroxide is added to 300 milliliters of 0.20 molar carbonic acid, will a precipitate of lithium carbonate form? Now, You might say, well, wait a minute, isn't lithium an alkali metal? I thought all alkali metal compounds were soluble. And that is the general rule of thumb, but you can see that the KSP for lithium carbonate actually has a measurable value of 1.7 times 10 to the negative second, which is not all that small of a value, but for alkali metal compounds, that's actually pretty significant. So anyway, if we are going to evaluate whether or not these concentrations are enough to produce a precipitate, we need to calculate the Q value for this. So the Q expression is going to be for lithium carbonate. We're going to get lithium ions, and there's two of them, so it's going to be lithium ion concentration squared times the concentration of the carbonate ion. Okay, so now we need to plug in values for that. And here's where we have to watch. Okay, the concentrations are a function of the volume that they're in. So we're taking 300 milliliters and adding it to another 300 milliliters. So effectively, we're doubling the volume, which means the concentration is going to cut in half. So rather than saying that we're going to have 1 molar lithium, we actually only have 0.50 molar lithium. Okay, now we're going to square that. Okay, so we can't forget that. The carbonate, again, same thing. We're doubling the volume that the carbonic acid is going to be present in, and so we have to cut that concentration in half. Again, that is a weak acid, so we're going to assume that it runs to the point where it's totally consumed, and we would end up at most with 0.10, I'm sorry, 0.10, because we cut the concentration in half, molar. All right, so that's going to give us 0.25 times 0.1. That gives us a Q value of 0.025. All right, and 0.025 is 2.5 times 10 to the second, negative second. And that is indeed bigger than 1.70 times 10 to the minus 2. So we would say that Q is greater than KSP. And so therefore, right, 3 dots, that means therefore a precipitate will form. All right, and PPT is your common abbreviation for precipitate.